Hello again. Today we will talk about methods to separate solutions and mixtures. And these are the most common methods, so filtration, chromatography, and distillation. Although there is also evaporation, but it's often not given just like here as a separate method because it's often considered to be part of distillation. Filtration is, I can tell you from personal experience, very much favored among university students, and that's because it's very cheap, it's very easy to do. There are not that many ways in which you can make a mistake. It's also very fast, but it has obvious limitations. So it's basically just a glass funnel and a piece of paper as a filter. It can be different type of paper. If According to the type of substance you're trying to separate, you can have different size of little holes in it, basically. So uh, when you want to pour something through the filter paper, the only thing that you're going to achieve is that whatever is solid inside your solution is going to stay in the paper, and that's called the residue, while the liquid part is going to go through the paper, and that's called the filtrate. Now, obviously, this separation method only works if you want to separate a solid from a liquid. So, something insoluble or something which has been precipitated. So, for example, if you want to separate sand and water, I can. When I pour the sand water through here, my sand is going to stay in my residue. However, if I want to separate salt from water, that's not going to work because whatever is dissolved is just going to go through the filter and go into the filtrate. Chromatography is a very specific separation method. Uh, you will recognize it easily in AP questions because it's going to involve a mention of a dye, a color, or a pigment. Basically, this is a picture of paper chromatography, which is the simplest type of chromatography. So, what chromatography is separating colors according to how much they stick to either stationary or mobile phase. So, in a paper chromatography, the stationary phase is paper, usually made of cellulose, which makes it polar, but don't make an assumption. Sometimes they will tell you that the mobile phase, which is this liquid wheel here, is more polar. So the paper is inside a beaker or any other type of container, and when you dip paper into water, what is going to happen is the water or any other liquid that you're using is going to go up, and you're going to let it go all the way up to here. And on this line, which is often called the baseline, you're going to put your pigment as ink or whatever else you're using. And then you're going to see after the liquid phase has have reached here that actually inside most colors you have more than one color. So you're going to see a separation of colors like this. Usually it's not going to look nice like this. I'll tell you that right now. Usually it's going to be just a lot of smudges. But what's important now is to define that there's a mobile phase, the whatever liquid is going up the paper, and there's a stationary phase. In this case, in case of paper chromatography, that's paper. There are other types of chromatography. We can also use a piece of glass with a gel on it, so it's gel chromatography, and there are column chromatography or others which are not that common in AP curriculum, and we will discuss them in a separate video. But what is important here is that uh, a yellow color has gone up the paper the most, which means that it is interacting more with the mobile phase. So the water or whatever the mobile phase is pulling it up, while the purple color is interacting more strongly with the paper. In this case, we use our famous uh, uh, rule that like dissolves the like. So if the mobile phase is nonpolar, that means that the yellow color is the most nonpolar, followed by green and purple. And if the paper is polar, that means that the purple is the most polar, followed by green, and then yellow. Most questions in AP curriculum are going to go along these lines. There is also RF, which is a retention index or retention ratio, is different ways to name it. It is basically uh, a number that shows how much uh, that specific color, how strongly it interacts with the mobile phase. So it's basically the distance traveled by that specific color, that specific component of our solution. Our solution is the color that we put here, right? So distance traveled by the component divided by the distance traveled by the solvent front, which is basically here. You stop, you just pull the paper out once it gets here. So if this number is close to 1, that means that the closer the number is to 1, the more that specific component is interacting or is attracted by the mobile phase, and the less it is attracted by the stationary phase. Distillation is the most complicated and also the most precise and most used, I have to say, separation method in chemistry. It's a very old procedure. I think they found distillation vessels from Egypt, from ancient Egypt, like 3,000, more than 3,000 years ago. I like to use this more complicated picture. So, what distillation does is it heats, it evaporates components of a mixture or solution. So in this case, as opposed to filtration, you can have a solution. You don't have to have an insoluble solid. So for example, if I put salt water in here into my distillation flask and I warm it up, what is going to happen is around 100 degrees or much earlier actually, water is going to evaporate. So the first step is evaporation. So the water is going to evaporate and go in here into the condenser. The condenser is cooled down by an outside supply of cold water. So this cold water just goes around this pipe and goes out, and its purpose is to cool down the vapor. So the vapor comes in here, cools down, condenses. That's the second step for distillation. So evaporation, then condensation, and then just goes down into my receiving flask, and that's called the distillate. And if I do that for long enough, my salt is going to stay here and my water is going to go in here. It also works for two liquids. Let's say alcohol, let's say ethanol and water. Ethanol's boiling point is, I don't know, like 60, 70, 80 degrees. So if the difference in boiling points between two liquids uh, is large enough, you're going to be able to separate them by heating this to the boiling point of the lower of the two liquids, and then alcohol was going to boil first, go in here, condenses, goes in here, and you got alcohol here and you got water here. Theoretically, however, in this case, the difference between the boiling points is just like 10, actually 20, 30, 40 degrees. That's not enough. So if you do this just once, you're going to end up with like 60% alcohol and still 40% water here. Because remember, even at 60 degrees, some water is still going to evaporate. So if you want to get a higher percentage of alcohol in here, you need to return this distillate here and do it again. I need to do it like 10, 15 times, and then you're going to get like over 90 something percent alcohol. So you don't have to return the distillate if you have a fractional distillation column. So a fraction distillation column is used in oil refineries, and what it does is basically just returns the distillate back into distillation multiple times without you physically having to do it. Also, when you're explaining when distillation is possible, the most common, most people will just say, well, it's possible as long as you have a difference in boiling points. However, in AP curriculum, please try to not just say different boiling points. Try to explain why the boiling points are different. In this case, like you have ethanol and water, they both have hydrogen bonds, right? However, water has many more hydrogen bonds. So that's why water has a higher boiling point. So just try to connect that as if possible. And yeah, you don't have to do this just only for 2 liquids. You can do like 10, 20 liquids as long as the boiling point, as long as their intermolecular forces are different enough. Here we have a little overview. So if there's an undissolved solid, you're going to use filtration. If you have two miscible liquids, like that dissolved into each other, you're going to use distillation. If you have any type of color, pigment, dye, you're going to use chromatography. And also evaporation. So when are you going to use evaporation? Well, if I want to remove the liquid but keep the solid, for example, if I'm trying to get salt from salt water, and I don't want to keep the water, so I'll just take the salty water from the sea, like seawater, right? And I'm just going to heat it and let the water evaporate and just keep the salt, right? So why? I mean, I could do this with distillation, but this is cheaper and easier and faster, and I don't need to keep the water, so I have no need to condense, right? Now let's try a couple of questions. So a student is given a mixture of sand and salt, basically, and he wants to obtain a pure dry sample of each of these. So how do you do that? So basically what you want to do is you can add water, and the salt is going to dissolve in water, right? And the sand is going to not dissolve in water. So then when you pour that through the filter paper, the sand is going to remain in the residue, and the salt and the water are going to go into your filtrate. And then you just heat this up, the water evaporates, and you get the salt. You also need to dry the filter, because it says dry samples. There's one more thing that I want to emphasize here. So, how if your purpose of your filtration is to obtain the residue and measure it, uh, the procedure is this. So you're going to take an empty filter, you're going to measure its weight, and then you're going to do the filtration. Then you're going to take the paper with the residue, because it's very difficult to separate the residue from the filter paper. You're going to take the paper with the residue, and you're going to dry the whole thing. And then you're going to measure the weight of that. And then you're going to dry it again. Why? Because you have to dry and measure multiple times to make sure all the water has gone. Once you get 2 or 3 measurements which are the same, then you know that all the water has gone. And then you take that number of now dry residue and dry paper, and you deduct from that the weight of the empty filter paper that you got at the beginning. That's the only way to properly in the lab calculate or measure the weight of the residue. So please keep that in mind. A mixture of 3 dyes separated by chromatography, blah blah. Okay, so the paper front is 8 centimeters, and you got the distances traveled by different colors and how to calculate RF. We said RF is this distance divided by the distance that the waterfront has done. So you just do that. In a paper chromatography experiment using a polar solvent, so the mobile phase is now polar, a dye A travels much more than B. What does that mean? Well, uh, a polar solvent pulls A faster than it pulls B. However, look at this. Identify the 2 phases. The paper is cellulose rich in OH bonds. So the paper has OH bonds, right? Cellulose is also polar, but cellulose is a huge molecule, so it's not really considered to be very polar, but it does have OH bonds. So if something is very slow here, in this case, like B, you can say that probably B is able to form hydrogen bonds, right? Right? However, since solvent is polar and A has gone higher, So A is something that's probably polar but cannot form hydrogen bonds, right? So you can discuss it like that, or you can say, so okay, cellulose is actually also polar, but not that much. But it is said in the right here in the question that a solvent is polar, so that must mean that the polarity of A is much more similar to the polarity of the mobile phase, and less so than the stationary phase. Okay, take a look at this. So now it says a solvent is nonpolar. What does that mean? So if a solvent is nonpolar, that means that paper is more polar than the solvent. That's how they ask these questions. So if the RF is high, that means that X has gone far with the waterfront and with the solvent front, which means that it interacts much more strongly with the solvent. And since the solvent is non-polar, that means that X has the least polarity, followed by Y, followed by Z. Most appropriate technique for all these. So sand stirred into water, of course, filtration, quick, easy, cheap. Solution of ethanol in water, as we said. So two liquids, two miscible liquids with different boiling points. So yeah, distillation and pigment. As soon as it says pigment, I'm just going to say chromatography. Propanone, boiling point 56, and water, boiling point 100. They're distilled. State which liquid is collected first and explain the difference in boiling point in terms of intermolecular forces. So, of course, the liquid with the lower boiling point is going to uh, evaporate first and go out first, go to distillate first. So water hydrogen bonds extensively. So water, as I said, you should think of it this way. So everything in water is included into a hydrogen bond. So each molecule has two OH bonds and two lone pairs. So it's a very, very strong hydrogen bond network. Propanone cannot hydrogen bond to itself. It is polar, and so it's dipole. It's mostly dipole bonds and in propanone. So that's the difference here, and that's why water has a higher boiling point. Basically, that's how you need to connect it, as we said before. Okay, take a look at this. So a polar solvent and a less polar solvent, and it says here that a strongly polar component interacts poorly with less polar solvent. So it's very logical, right? So if our dye is very polar, of course, it's going to go way higher with the polar solvent, with the polar mobile phase, right? And way less with a non-polar or less polar mobile phase. So why a student cannot separate salt from the water and seawater by using filtration. So, as we said, the thing about dissolved things is uh, we talked a lot about this. So the particles of whatever is dissolved are separated, and if the particles are separated, then they're very small, and they can go through the holes basically in the filter paper. However, if something is insoluble, then its own molecules and atoms stick to each other and form much bigger chunks that cannot go through the filter paper. Okay, a student sets up a paper chromatography experiment. After 20 minutes, nothing has happened. So, if you set a chromatography experiment like this, with your dye, you put your dye under the solvent level. What is going to happen now? I mean, usually, as we know before, I mean, you usually want to put your color here, your dye here, and you could put it anywhere above, technically, right? But if you put it below like this, it's just going to dissolve in the solvent, right? Or create a huge smudge in the paper. So that's the error that the student has made. Hey, practice this and good luck.